So, we are going to talk about how to use matrices to program first in 2D. We're going to talk about it in 2D, and then we're going to talk about it in 3D. And we're going to focus first on the letter H. And we're going to modify the letter H using matrices. So we're going to write the letter H in terms of its vertices. It's a nice letter, so it'll be fun. Oh my gosh, I just touched the computer screen with my finger. If something would happen. Okay, so if we write the letter H in terms of its vertices, first I'm going to sketch it. How wide do we want to make it? How does this sound, like this? So we're going to name it in terms of its vertices. So let's start in the origin. So that's 0, 0. And then let's go to 0, 2. So I'll go 0, 0 to 0, 2. And then I'll go back down to 0, 1. And then I'll go across to 1, 1. And then I'll go up to 1, 2. And then I'll go down to 1, 0 to create my H. So you could have done this a number of ways, but if I go up, back down to the midpoint, across, up, and then back down to the lower right-hand corner of my H, I'll cover all the lines in a way that I don't end up crossing in a weird way or creating like an O or anything else. So there's my H. Any questions on that? We could call the matrix H too. What's that? Okay. So if we take the matrix and multiply it by that matrix, what happens to the H? Any predictions? Okay.
Or actually, it would get shared, but it would go down. Well, it wouldn't go down, but it would shrink.
Oh, there's a lot of things you said right.
Wow.
Ben?
So it would keep all of your x values the same, but it would multiply. No, it wouldn't. It would add your x value to 1/4 of the y value to produce a new x. So it would shift it to the right. Yes, it would shift it to the right.
All the coordinates?
Well, all the non-zero ones.
Okay. So they'll shift all the non-zero ones. And do you remember what we called that? Yeah, we called it a share. Did anyone accomplish the matrix multiplication yet, or are you just waiting? Scenario, you're doing it?
You don't have to go. Yeah, you just go on the shoulder.
Okay, Ray, what is that?
Everything right. So it's 0, 0. You're just getting your career ended by the future. That's right.
5, 0,
Okay, and what's the top row, Ray?
Oh, 0, 0, 0, 0, and then 1.25, 1.5, and 1.25.
So you say the first are all zeros?
0, 0, 0. The zeros would stay zeros, right? was just thinking you do it geometrically.
Right, and that was all due respect. I, from the bottom of my heart, respect doing your math and really just want to give you a little bonus there, but, okay, so 0, 0 stays 0, 0. But I'm gonna have you guys do it because you're just staring at me waiting for me to do it.
Yeah.
You're the one to go. You're doing it. That makes me happy.
I think I might disappoint a little bit.
Oh.
I'm not gonna do well at all, so
You're
just
using
think-
us.
It seems too easy, which makes me.
Let's just remember that there are people that will watch this later and not understand the context of your comments, so.
it do not matter.
I feel like I know what I'm saying.
Ideally, in years in the future, I won't have to re-record and.
No.
That is awesome.
They're gonna keep me like we weren't.
And then they'll be like, oh, I wonder who the person is who isn't good at things is. That.
I don't think you're gonna be this one.
I'll just keep it for the court document.
Can you reuse like next year's class instead?
I feel like we've got to be one of the most dysfunctional.
I would absolutely.
Yeah.
Depends on the lens, what you're changing function of this function.
Well, it's not even good. This is so hard.
Okay, I'm glad I don't feel the only side issues. I don't know.
When
Maybe
they're talking
it's
about the
just
matrix,
wrong.
that's from.
Robbie's just not gonna do it. Oh wow, Robbie, you're so cool.
I just don't.
Is this Lisa?
Does anyone have it?
Alright, Robbie has had it for like years apparently, and I think I got it.
Or does anyone want to state their answer?
So,
Right, go for it.
Redeem yourself.
whatever. 0.5, 0.25, 1.25, 1.5, 1.
Yeah, that's right.
About 50 cents.
Good work,
But I meant if you drew it out geometrically, like on the, if you just wrapped it, you could just take that word and shift it.
Well, let's draw it out.
don't have to,
So 0, 0. And then I go 1/2.
2.
See how that looks? 1/4, 1. So that is the left side of my H now. And then from here, ooh, this is 1 1/4.
This is totally
Alright, so what did I do to the H? I mean, we called it a shear, but if I were thinking of this in terms of computer graphics or even typeface, what did I do?
You italicized it.
Yeah, I italicized it. How do you spell italicized? Now, is that a true italicization?
No.
What would need to happen to it? How?
Oh, wow.
How would you have to change the font?
Oh, on the bisector?
You can still italicize text.
You also stretch it.
Like, I don't care about.
So- consider this, it is italicized, but does it appear to be a little bit different from pure italicization?
Doesn't have to be thinner.
Yeah, it has to be a little thinner. Normally when we italicize, it doesn't get that much wider. So let's thin it. So how would we scale it?
Would you do like a 0.25 at the bottom?
You wanna make it to 3/4 of the size? You wanna do it to 1/4 of the size?
I'm not sure.
So if we go out, where do you want, because the bottom, is within the range of what it was. It was at 1/0, but the top is now at 1 1/2, which is quite a bit wider than it was. It's 50% wider. So where do you want it to end in terms of its width?
2/3.
You want to be 2/3 as large? So you want it to end at the 1. Okay, so if we're going to scale this at the 2/3, what is that scaling matrix?
2/3, 0, 0.
Okay. Times. Oh, I don't have this one done ahead of time. Let's see. They're scaling it. I go, those are the 3, 5, 6, 1, 1, 2. Ooh, that's pretty. Just a little italicized H. Doesn't it look less like fat butter? You can't have your font just increase 50% and you italicize it or else nothing will fit anymore. Okay, so we accomplished italicization given matrix multiplication of font. How's it feel? I think it's awesome. All right, so does anyone want to read about Mobius? Okay, Mark?
In mathematics, homogeneous coordinates or projective coordinates introduced by August Ferdinand Mobius are a system of coordinates used in projective geometry, as Cartesian coordinates are used in Euclidean geometry. Formulas involving homogeneous coordinates are often simpler and more symmetric than their Cartesian counterparts. Homogeneous coordinates have a range of applications, including computer graphics and 3D computer vision, where they allow transformations and, in general, projected transformations to be easily represented by a matrix.
Thank you. So, we're first going to talk about homogeneous coordinate mapping. And then we're going to talk about applications to computer graphics tomorrow. Because as you all know, when we started off with computer gaming, we went from 2D representations, that would be Pac-Man, Pong, Donkey Kong, those were all 2D, to now, when we view things, we're viewing something on a 2D surface, and it appears three-dimensional. How is that done? It's done using linear algebra, and how to make something appear three-dimensional, even though it's on a two-dimensional screen. Okay, so we'll talk about how that's accomplished tomorrow. So points in R2 are projected 1 point above the XY plane in R3. So we're first going to talk about how to map to R2 onto R3 by just having it hover above R3, or above the XY plane in R3. And so the transformation goes by taking a matrix, which was in R2, that's matrix A, and now you are putting it into R3 by using a partition matrix where A is a 2 by 2, and then you just throw a 0, 0, 1, and this then is a 3 by 3 matrix if you consider filling in all the actual values. So it's just kind of ingenious, it's almost genius mapping. So for example, if A was what Ray suggested it be, where we were able to scale all the x values by 2/3, A would map to a homogeneous coordinate, and that would be then 2/3, 0, 0, 0, 1, 0, 0, 0, 1, and that's the homogeneous mapping of A, which is in R2, into R3. So now you have the homogeneous coordinates. So here's A. Questions on that? What's your best? Okay. So if we wanted to do a projective transformation matrix, we're scaling by a factor of 1/2. Let's say we're scaling both the x and the y coordinates. A in R2 would be 1/2, 0, 0, 1/2. But if it's a projective transformation matrix, it's 1/2, 0, 0, 1/2. But since it's a projective transformation matrix, it's a 3 by 3 that projects 1 unit above the XY plane. So that's what that looks like. Questions on that?
Are we left to ask some questions the other day,
What about the triangle?
No. When they ask for the numerical value, like, does that mean the part that isn't attached to the I? For the last one. You do.
It's just what's the value of it.
You just got a computer's fast.
I mean, are we allowed that?
Well, I'd like to continue teaching.
All right.
The triangle one, I mean, it should be inside of the triangle for the triangle one, not on the edge. And 6,
Oh, I don't.
it was really close to the edge. Well, I really need to delete this. But you should get a value. There might be more than one. Okay, so what would we get for rotating pi over 2 clockwise? Do you guys remember the matrix for that? Right?
The 0, 1, -1, 0.
Close.
zero, negative one?
Remember, it's cosine, negative sine. Yeah. Sine, cosine. That is A, so it's 0, negative 1, 1, 0. And then you transform it so it's floating 1 unit above the xy plane. Yes.
Sorry, so these matrices are just different from the normal transformation matrices because they're like homogeneous coordinates, which are different how.
So instead of, it's a mapping from R2 to R3,
Okay.
and it's mapping them from being in R2 to being in R3, and now they're in R3, floating 1 unit above the xy plane
So that's always true for
homogeneous mapping, or for a projective transformative matrix. I'm sorry, transformation matrix. Yes.
So you could just do like, the projected transformative, it could just be zeros on the outside, but then instead of projecting it onto the plane equals 1 above the xy, you'd just be putting it on the xy. But it would still be R3.
If it was all zeros?
Yeah.
Yes, but the homogeneous mapping, the convention is doing 1 unit above the xy plane. So it gives it kind of dimension. Uh-huh.
isn't the rotation matrix for rotating it counterclockwise? So would it be the opposite sign?
So this should be negative pi over 2. So the cosine of negative pi over 2,
Yeah, the two of those. It's all one.
all right. So this is plus minus.
Oh,
Awesome. Thank you.
Huh, so I was right on that.
All right,
Wait, why?
raise back in.
Wait, no, wait.
Yes.
I don't, I'm gonna have that work. It's like, how do you get
The
like
rotation
positive
matrix.
one, negative one, and then one? Like, how do you get like that? How do you just
I'm
not
pointing
get?
at pi halves.
Two things.
Okay.
Negative pi halves.
Sorry.
Like, I don't get how you transform,
For this part,
well, like every, yeah, please.
okay, so we're gonna plug negative pi over 2 in for theta
Right,
and evaluate the sines and cosines, and we get this.
right. Like, only for the first little square.
Yeah, and then the outside for a transformation matrix, transformation projection, is you're projecting a 2D matrix onto a 3D space. So you're projecting it so it's floating 1 unit above the xy plane.
So it's always like 0, 0, 1, and then 0, 0, 1.
It is, yes.
Okay.
Except right here. Remember how we weren't able to do translations?
Oh, right, yeah.
So this is the translation matrix.
What's that?
Yeah. I should probably write that differently. Each unit's horizontal. Oh, geez. Who knows? Thank you. Okay, so if we take the matrix out of the 2D plane, we can translate. We couldn't translate if we kept it in the 2D plane. So this is how we translate. We can translate with a projective transformation matrix. where H is horizontal units and K is vertical units. So to translate up to and one right, here's the matrix. So if you want to move left, H would be negative. If you wanted to move down, K would be negative. So that's really a nifty turn of events.
But this only works if you're at 1 unit above this thing.
But then you can just put it back.
No, I know, but like if you're at like 2 units above this, then you have to
It's
shift.
like, okay, Charlie had a friend, not a friend, an acquaintance that lost in Foursquare and wouldn't leave the Foursquare.
Oh, you're talking about your son, Charlie.
Yeah.
Okay.
So he picked her up and moved her out of the Foursquare. So he translated her 1 unit above the 2D plane, moved her, and then translated her back down.
Did he actually do that?
Yes, and then lied. Never admitted it. I was like, I'll get him to admit it. He said, I can't recall what occurred today. Literally. First grade.
That's such a finesse. Like that's exactly what you're supposed to say. I don't remember. Like
It was Friday.
I can't recall.
Yes.
And then
First grade. And I asked him that day. It wasn't like,
How
I
old
was
is he now?
Well, he's a 6th grader. So
Oh,
imagine
years ago.
my life now. When you can lie well and finesse wise, it's like,
how did you know that? Like,
Anyway.
that's exactly what you say. I don't want to get into it. I don't recall.
it's like he watched Clinton during the bad things. He did not, by the way. So anyway, this is exactly what happens in translation matrices when you essentially pick the matrix up 1 unit off, translate it, and then you translate it back into the 2D plane. So it is, but it works.
That's not going on.
Oh, wow. What time? Oh, yeah, we have time. Awesome. Okay.
We can do it tomorrow.
Michael, what you guys have been going?
To what?
Hey, didn't you guys see it?
Tomorrow.
No, now it's done.
What time is it? I just heard 3:04.
Yeah, hand it in, gentlemen. Let's go. We got 10 minutes.
I think.
Yay.
This is right here.
They're not writing.
One.
Okay, hand it in. All right, can you guys write the coordinates of the shape, please?
I thought that was.
Okay, thank you, everyone, for playing along. We are going to accomplish a scaling by a factor of a half, rotating. Did it say clockwise? Yeah, here I have counterclockwise. Bummer. Okay, well, we'll do clockwise. And then translation. And we're going to do it on this shape and see where it ends up. So let's write the coordinates of the shape. We'll go around clockwise. We'll start at 0, 0. Okay, and I can write 0, 0 again, but I'll just assume that I go back to the origin of that. Now, do you guys want to accomplish the translation piecewise, or do you want to multiply all 3 of them together and do it all? Oh no, we'll do it piecewise. We'll do it with the calculators, okay? Because we don't want to do it by hand. Okay, so first we'll scale. So that's stage 1. So scale was 1/2, 0, 0, 0, 1/2, 0, 0, 0, 1. So go ahead and scale.
What?
So we're going to do the projective transformation.
Just add your own.
Well, that's what we wrote. That was the whole point of all this.
But like, how do you multiply the matrices? So it's not working by.
Oh, sorry. So what we need to do
Oh, yeah.
is we are going to float this one above the XY plane to be able to accomplish our goals. So we're gonna do the homogeneous coordinate mapping. That's a homogeneous coordinate mapping. That feels like cheating, but that's what it is. Okay. So this one we don't really even need to calculate because we're just taking all these and having them. Okay, so I'm making everything have a big, and so we're gonna pretend this is out half.
Oh, that's weird.
So the big boot became a little boot. All right, are you guys down to rotate? Okay. That sounded weird.
Good.
Are you guys?
Really good.
All right, come back around. That's the best of me. So let's rotate. Pi over 2 clockwise. And that one was 0, 1, negative 1, 0, right? I'll put it right here. Okay. I don't trust myself to do this. Did anyone do it right?
Oh, I had a question. So the three, like, you don't actually need to add the third row for any of the scaling except for the translation, right?
Technically, no.
Okay.
So mine was actually wrong on my paper. I have it counterclockwise. So I'm really counting on you to do this.
Right.
So if you just flip R1 and R2 and magnetize R1,
Rotating pi over 2 clockwise.
so
Oh, I'm so bad.
So the,
Almost there.
you want the point?
Yeah.
Yeah. So the 0, 0,
Gotta keep going.
3 has 0.
Negative
Yeah.
negative 3 halves, 0 half. Negative 1 half, 1 half. Negative 1 half, 1.
no, you're flipping this up.
Yeah, right. The negatives are all the positive ones. The
How
top
do
is all positive, the
you
bottom is all negative.
think?
Yeah, I had it right.
What's the last one?
Negative 1.
0, negative.
Okay. So 0, 0. 3 halves, 0. 3 halves, negative 1 half. 1 half, negative 1. 1/2. 1/2 negative. 1. Oh, Lord, where did I go?
Oh, that's fair.
Yay!
Hey,
We rotated 90. Sorry, math works. It should, but my facial reason is so bad. And I was like, ah.
not bad, you guys.
Alright, oh, we gotta translate.
That's fair.
Alright, translate. Here's the translation matrix. Oh man, I'm running out of colors. Oh, holy cow. Alright, well, let's do it. Translate. Okay, 1 0 1 0 1 2 0 0 1. Yeah, use a calculator for that.
Robbie, can you do it without a calculator?
Okay.
Great.
Yeah.
Do we raise?
Okay. What do you think?
Give me 2 seconds. What? Okay, Robbie, let's raise.
Okay.
I need like purple.
Right,
Yeah,
very
I
low.
like
It's just going to be 1, 2, and then 5 times 2, and then 5 times. You just add.
Yeah,
You add one.
Come on, Mark.
Wait, Robbie, I'm
Oh,
gonna beat you.
duh.
You can just
Okay.
add. You don't need
Oh, why is it not purple?
I'm not gonna beat you. Does it matter?
What'd you get?
Yes.
No, you didn't. What's the second column first entry?
Second column, first entry, second.
What's the fourth column second entry?
Ha ha!
Entry is 3 times.
Yeah, you do.
It's not. You just take two.
Okay, it was 1 right and 2 down, right?
Yeah. It's everything the same now. And then you can run it.
So move it 1 right and 2 down. Okay, it's not that hard, sorry. I could just move it 1 right and 2 down, but.
Okay, what's the first entry in the first column? Second entry in the first column?
You're on a ball.
Second entry in the third, or third entry in the first column?
Mentally.
1.
I don't see a problem with that.
Second entry in the second column.
Like,
Two.
like mentally.
Third entry, or second entry in the third column.
Like that way, really, not that way.
Okay, here we go. I think this is
Oh,
good.
you're too good.
I'm literally adding numbers.
Me too.
You're too good at that.
0 2
That's scratching the first thing.
0 2 5 halves, 2.
Oh my god. I will show you. Yeah, I guess
Why is it over so much?
Wait, isn't the paint from your own car, though?
What did I
No.
mess up?
Oh, it's 1,
It's
2, not
from
0.
my-
Yeah.
It's from a scratch. It's
Oh,
a
such
scratch.
a scratch.
1 2 5
Why
halves.
don't you?
I remember
Why
you
would
were
you also have Mario?
It doesn't really come off very
Because you have the 2
Okay,
over
right,
it says
scratch.
scratch.
Oh my god. No.
Wait, what is
It's
it?
not a scratch from the paint.
Hey, how did you get this scratch? How did you make your
Alex is
garage?
like, I have a weird trick on the garage, so I like.
And you
Alex
just,
is like, it's
flip the
elevated
door?
above
Yeah.
the normal paint, thus.
It is. Nadia Ganesan, Emma Prislov, Mikey Lon, Sylvie Arnold to the College of Police.
Seriously, follow me out the car. I will show you.
Well,
And
that's good.
like, this is your mom.
Yeah,
I
Follow
think
her
I
out
can see
to the
that
car.
today.
And she tells me. Yeah, it does sound. We want to
Little
this
sucks.
one.
Why
Okay,
you
but the
call her
reason I have.
Yes, we crossed your side. Good work.
What happened?
I got
That's the correct.
my motor.
Right. Those are the only ones doing gays.
I just like instead of flipping it, I
If
just
you
kind
move
of
that left one down too.
I was explaining to Marta, right?
We're done! It worked! It translated!
Dude.
Over 1 up 2.
I was saying instead of flipping it, I just kind of like
That's for WMO.
threw it across.
That was a struggle.
Yeah.